This is Dr. VVSH Prasad, Professor of the Department of Mechanical Engineering, and I am here today introducing the subject Thermodynamics, which is the core course, foundational course in the Mechanical Engineering. And the course objectives, the students will try to learn the fundamental knowledge on concepts of physics, chemistry for obtaining the axiomatic principles using the thermodynamic coordinates. Here, axiomatic means they are the truths and principles based on the observations, the laws of thermodynamics have been formulated. The thermodynamic disorderliness in the real-time physical systems like external or internal heat engines, heat pumps to get the measure of performance characteristics. When you see this, definitely there is an ever increasing demand on the internal and external engines to improve the performance by minimizing the fuel consumptions that we measure in terms of the measures of performance characteristics. Then here also we will try to understand the performance characteristics of open and closed systems of the thermodynamic cycles for effective delineation of real-time applications. That is how the turbochargers, superchargers have come into picture to improve the or to convert the heat energy into mechanical energy. The thermodynamic cycles such as power, refrigerant cycles to yield alternative solutions to conserve the environment. That is the reason there is an ever requirement to minimize the release of the CFC gases into the environment so that the global warming can be reduced. So the framework of these course objectives will drive the students to understand the environmental importance, that is the environmental protection by way of minimizing the emissions through the heat engines and also other alternative systems. These are the course objectives. The students will try to learn these aspects in this course. Thermodynamics is a branch of science, phenomena of energy and related properties of matter, especially laws of transformation of heat into other forms of energy and vice versa. This is the definition of thermodynamics. Phenomena of energy and related properties and the related laws of transformation into heat and other forms of energy and vice versa. Basically, here we take any coal. It has got a chemical energy that is being converted into heat energy, and again that is converted into mechanical energy. That is how the forms of energies are being taken place. That mechanical energy again converted into electrical energy in a power plant. Again, if you take the petrol engine, the chemical energy is converted into heat energy through combustion. From that, the heat energy is converted into mechanical energy. Then in turn, this is added to any mechanical system for doing the useful work. So thermodynamics is a basic and important subject. It is not confined only to the IC engines. It is a broad spectrum which is also applicable in the aerospace applications. There are two approaches for studying the thermodynamics. Macroscopic, that is called classical thermodynamics. Study large number of particles or molecules that make up the system or substance in a question does not require knowledge of the behavior of the individual molecules. That is, we call, in a broader sense, large particles we will handle, then we call it as the classical thermodynamics. In this subject, we deal with the macroscopic approach of the thermodynamics. Microscopic or statistical thermodynamics concerned with the individual behavior of individual particles, particularly molecules. Study average behavior of large group of individual particles. So this microscopic approach deals with the chemical thermodynamics. So in a sense, the thermodynamics is broadly classified into two categories, macroscopic and microscopic. Microscopic approach is the major area where we deal in the fundamentals of thermodynamics. Further, when you look at it, the approaches, in this approach, a certain quantity of matter is considered without taking into account of the events occurring at the molecular level. In other words, this approach of thermodynamics is concerned with the gross or overall behavior. This is known as classical thermodynamics. A similar, what is the definition on the microscopic approach is, the approach considers that the system is made up of very large number of discrete particles known as molecules. These molecules have different velocities and energies. The values of these energies are constantly changing with time. This approach to thermodynamics, which is concerned directly with the structure of the matter, is known as statistical thermodynamics or chemical thermodynamics. This is the fundamental definition at molecular level and gross level or overall level. The analysis of macroscopic system requires simple mathematical formulation, whereas the behavior of the system is found by using the statistical methods, as number of molecules is very large. So advanced statistical and mathematical methods are needed to explain the change in the system. Then the values of properties of the system are their average values, not individual. For example, consider a sample of gas in a closed container. The pressure of the gas is the average value of the pressure exerted by millions of individual molecules. Similarly, the temperature of this gas is average value of translational kinetic energies of millions of individual molecules. These properties like pressure and temperature can be measured very easily. The change in properties can be felt by our senses. The properties like velocity, momentum, impulse, kinetic energy, force impact, which describe the molecules, cannot be easily measured by the instruments. Our senses cannot feel them. Next, in the macroscopic approach, if you look at it, in order to describe a system, only a few parameters are needed and that are enough, whereas large number of variables are needed to describe a system. So the approach is complicated. With this definitional understanding, we can see what is the difference between macroscopic approach and microscopic approach. Then comes, what is a thermodynamic system? A thermodynamic system is defined as a quantity of matter or region in space which attention is concentrated on the system of a problem. And when you look at it here, this is thermodynamic system, and the outer phenomena we call it as the boundary and surroundings. This is thermodynamic system, we consider it as. And everything external to the boundary is called the surroundings or environment. This is boundary, surroundings or environment. Okay. The system is separated from the surroundings by system boundary. The boundary may be either fixed or moving, and these boundaries can also be further classified into uh, adiabatic boundary, then diathermal boundary. Like that, the boundaries also will have a significance in the thermodynamic system. A system and its surroundings together comprise an universe. Then what are the types of systems we come across? One is closed system, open system, isolated system. When you go with a closed system, energy, not mass, crosses closed system boundaries. Means, if you look at it, only energy transfer takes place between system and surroundings, and there will not be any mass transfer that takes place. Okay, and here mass is constant. And if you see, this is the closed thermodynamic system and this is the boundary, and beyond the boundary everything is surroundings. Okay, so when you see here, thermodynamic system, that is thermodynamic closed system, boundary, surroundings. So in this, when you consider only energy transfer is taking place, there is no mass transfer is taking place. Such a system we call it as the closed system with fixed mass. Then comes open system. In the open system, if you see, this is the control volume and this we consider as the thermodynamic system, and this is the boundary, and this is the surroundings. Okay, thermodynamic system, boundary and surroundings. In this case, compared to the previous closed system, in the open system, both mass and energy transfer takes place between the system to surroundings. Such a system we call it as the open system. And when it comes to a system where, in this one, this is the thermodynamic system, there is no energy transfer across the boundary to the surroundings or from surrounding to the system. Closed system where no heat or work energy may cross the system boundary. Okay, surrounding system, and this is the boundary. So here we can see very clearly there is no energy or mass transfer is taking place in a isolated system. Properties of a system. Any characteristic of a system in equilibrium called property. Okay, there are two types of properties we come across: extensive properties, intensive properties. Extensive properties vary directly with the size of the system. Example, volume, mass, total energy. When you say here, I can explain you, there is 1 mole of H2 hydrogen, 1 mole. There is 1 more mole of hydrogen. When you put together, if you add them, then it becomes 2 moles of hydrogen. So when you see here, these 2 moles are getting added. So there is volume change is taking place. Volume change is taking place. And here we can say 1 kg plus 1 kg. When both of them added, it becomes 2 kgs. Such properties we call it as the extensive properties. Then when we see here, there is intensive properties and are independent of the size of the system. Here it is dependent directly on the size of the system. A container with 2 moles. Okay. So the volume, here you can say volume is a extensive property. Intensive property, when you consider here, there is one system with 1 meter cube. Then there can be another system with 2 meter cube volume. But here, if you do the measurement of pressure and temperature, if you make these pressure and temperature, say 1 bar and 100 degrees. Here also it can have 1 bar and 100 degrees centigrade. So if you see, pressure and temperature are not dependent on the size of the system. It is independent of the system. And it is that property we call it as the intensive property. Okay. And how to define the extensive properties per unit mass are intensive properties. Okay. Specific volume, volume by mass, density, mass by volume. These are all intensive properties. Extensive properties per unit mass are called intensive properties. These observation of properties of a system should be very clear. That properties, as you look at it, extensive and intensive. In the extensive, per unit mass will become a intensive property. State of the system. State of the system, I can explain you through a Cartesian thinking. Instead of volume, it can be X. Instead of pressure, it can be Y. But if you wanted to have any point that is to be located, you need the X value as well as the Y value. Similarly, in any thermodynamic system, you wanted to have the state of the system, then you should be able to specify the particular volume and pressure in the thermodynamic system. Means, instead of Cartesian coordinates, we can call them as the thermodynamic coordinates. It is the condition of the state as defined by the values of all its properties. All properties of the system are known and are not changing. If one property changes, then state of the system changes. That is, the state of the system is condition of the system as defined by the values of all its properties. Maybe pressure, volume, temperature, whatever it may be. What are the, when do you say it is a thermodynamic property? In the previous aspect, what we have seen is a property is the state of the system. Okay. Then when do you say it is a property? Then a thermodynamic property is a characteristic which can be used to describe the state of the system. The essential features of the property are: a thermodynamic property should have a definite value when a system is in a particular state. Definite value, that is pressure, temperature, volume, entropy, enthalpy. Like that, there are many thermodynamic properties are there. So you should have a measurable value. And change in the value of property should not depend on the path followed by the system in reaching the specific state. In other words, the change in the property depends on the initial and final state of the system only. That is the change in the property, where you can say, if you look at it here, integral dz from state 1 to state 2 is delta z, z2 minus z1. That is, a thermodynamic property is a point function or state function, and it is not a path function. So if you see here, P and V, when you go from here to here, 1, 2, 2, so the path is like this, but it will have at 1, you will have the coordinates as P1, V1, here V2, V2. So whatever the path you take, say even if you take this path also, the volume and pressure will not change. So that we call it as the property is not dependent on the path it follows, but it is the property at which it exists. Then mathematically we should define thermodynamic property is a point function. This is a thermodynamic point here, and here also a point function. And if z is function of x and y, then if you partially differentiate with p and v means it is x and y. Dz is equal to dou z by dou x, keeping y as constant with respect to x, and dou z by dou y, keeping x as constant into dy. Then it can be written as mdx plus ndy, where m is defined as dou m by dou y with respect to x, and dou n by dou x with respect to y. If dou m by dou y is with respect to x is equal to dou n by dou x is equal to y, if they are equal, then dz is an exact differential, then z is a thermodynamic property. Then z is a thermodynamic property. Hope that you have understood how to define a property in a thermodynamic system. Say here x and y we have written means it is say volume and pressure. It is volume and pressure. Okay. So a property is defined when it is mathematically, it is an exact differential. It is an exact differential. Definitely, we are understanding about a thermodynamic system with the following expression has been suggested for differential of the pressure. And this is an equation that is taken from the van der Waals equation, where dp is equal to r into dt by v minus b minus rt by v minus b square minus 2a into v cube into dv, where T is the temperature, V is the volume, A, B are our constants. A and B are called as the van der Waals constants or coefficients, and where R is called the universal gas constant. From this, we can judge whether the dp is an exact differential or not. If it is exact, find the relation between PVT. Then when you see from the expression, P is the function of temperature and volume. P is the function of temperature and volume. Therefore, in the previous slide when we have written dz is equal to mdx plus ndy. Similarly, we wanted to write this as the dp is equal to, where m is equal to dou p by dou t when volume is constant and differential is taking place with respect to dt, dou p by dou v when temperature is constant, differentiation is taking place with respect to v, and then we call it as the m dt plus n dv, n dv. Okay. Therefore, where m is equal to dou p by dou t when volume is constant, n is equal to dou p by dou v when temperature is constant. The given differential pressure is this. Okay. Then m is equal to r by v minus b, n is equal to minus rt by v minus b square plus 2a by v cube. These are the coefficients. R by v minus b is the dt coefficient and this is dv coefficient. Then what is our exact differential? It has to satisfy dou m by dou v with respect to temperature is equal to constant and dou n by dou t when volume is constant. Therefore, dou m by dou v and dou n by dou t, when you do the differentiation, both are equal. That is r minus r by v minus b whole square minus r by v minus b whole square. Then definitely the given expression dp is an exact differential. This is how we are going to find out in any given problem whether it is an exact differential, whether it is a property or path function. So therefore, the given expression that dp is equal to r dt by v minus b minus of rt by v minus b whole square minus 2a into v cube into dv is a property. With this one, we can judge. Therefore, the problems pertaining for any expression, it is a function of two variables, then we express in terms of our m dx into n dy and verify their partial differentials. If they are equal, then that particular governing equation is a property and it is an exact differential. Then we will go for the what is a process. When a system changes from one equilibrium state to the another one, then some special processes are also there. Isobaric, constant pressure process, isothermal process, constant temperature process, isocharic process, constant volume process, adiabatic process. Okay, that is a process. Beyond this also, isocharic, isobaric, adiabatic, and here we are going to have the another process, that is polytropic. Okay, then what is process? If a thermodynamic system is there at point A and it has followed a path to point B through this, and the thermal coordinates are P1 V1, P2 V2, the path taken from A to B is called as the path and the volume is changed from expanded from V1 to V2 and pressure is reduced from P1 to P2. The path taken from A to B is called the process. Okay. Then a series of states which a system passes during the process, that is called path. This is the path we call it as. Then what is the difference between a path and cycle? Then we say here we have got two processes. 1, A, 2. One process from system from here to here it is going. Then there is one more process, that is 2B1. So it is moving from here to here. Okay. The process are a series of connected processes with identical and end states. When the system has taken from 1 to 2, from 2 to 1. But here these two states, they will contain the properties. 1, A2 is called path, 2B1 is called path. From 1A to B1 is called cycle. It is a cyclic process. It is a cyclic. A process or a series of connected processes with identical end states. We call it as the cycle. Then thermodynamic equilibrium. Okay. What is a thermodynamic equilibrium? A system is said to exist in a state of thermodynamic equilibrium when no change in any macroscopic property is registered if the system is isolated from its surroundings. Then we call this as the thermodynamic equilibrium. Okay. Equilibrium indicates the state of balance. In equilibrium state, there are no unbalanced potentials within the system. Equilibrium is classified into, there are three types of equilibriums we classify. Mechanical equilibrium, chemical equilibrium, thermal equilibrium. In the mechanical equilibrium, it possesses uniform pressure. If there is no unbalanced force in the system is said to be mechanical equilibrium. If an unbalanced force exists, either system alone or both the system and surroundings will undergo a change of state till mechanical equilibrium is attained. Means in a thermodynamic system there is no pressure variation in the system. Then we can call it as the mechanical equilibrium. Chemical equilibrium. If there is no chemical reaction or transfer of matter from one part of the system to another, such as diffusion or solution, the system is said to exist in the state of chemical equilibrium. Means if the combustion is taking place, there is no chemical equilibrium and there is no pressure equilibrium unless uniform pressure, and if there is no combustion activity taking place, then it is not having even the chemical equilibrium. Then thermal equilibrium, uniform temperature. When a system existing mechanical and chemical equilibrium is separated from its surroundings by a diathermic wall, diathermic means which allows heat to flow, and if there is no spontaneous change in any property of the system said to exist in a state of thermal equilibrium. It means uniform temperature. So, in a thermodynamic system, it will have three equilibriums: mechanical equilibrium, chemical equilibrium, thermal equilibrium. Then, what is the state of the system? Quasi-static process. Quasi-static process means there is a gas and there is a piston and there are some weights are there. Okay. System boundary and initial stage. Okay. And it has got certain weights and it reaches up to final stage. And stops are there on the system. Okay. Then from initial stage, it keeps on moving to the final stage. During moving, then what we have done, instead of weights we have written, instead of that, if you keep a heap of sand particles on the piston and you keep removing one particle or after other particle, the initial state of system will reach to the final state very, very slowly, and the intermediate states are also considered to be equilibrium states. Then what is the equilibrium state? The equilibrium state, as just now we have discussed, there are three equilibrium states that will exist. One is mechanical equilibrium, chemical equilibrium and thermal equilibrium. Means pressure, then temperature, and also the other parameter. Other parameter, what we have told? Chemical equilibrium. There will not be any chemical reaction that takes place. Means initial to final when it is moving, there can be some sort of an intermediate equilibrium states. And if you keep adding the sand particles once again, and you take the system from the final stage to initial stage, again you will get some of the equilibrium states, and this process we call it as the quasi-static process. And the process can be taken from initial to final, final to initial, and this process we call it as the quasi-static process. But in the real time there is no quasi-static process. All the systems in the open system, they are spontaneous. They are all spontaneous. Okay. And in the next lecture, we will see how the temperature variations are taking place and what are the international standards of the temperatures. We will discuss about it. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.